An involution is a permutation that has reflective symmetry over the diagonal y equals x. We will consider sets of involutions that avoid specified patterns. We use this notation, and we use the subscript n to denote those involutions of size n. This allows us to define the exponential growth rate of an involution class in the same way that we do for permutation classes. The most important question to ask whenever you see a limit is, does it exist? In 2015 with Miklós, Bóna, Cheyne, Homberger, and Vincent Vatter, we looked at some of these involution classes where B contains a pattern of length 4. Here's a table showing part of the counting sequence for 7 such classes. 2 of the growth rates at the bottom were already known. 2 more we were able to calculate exactly. The dark blue box on the right is for involutions avoiding 1 through 2, 4. In this case, we couldn't even show that the growth rate existed. All we did was give some bounds for the lim sup of the same sequence. In the case of regular permutation classes, any class that avoids a single pattern has a growth rate. If beta is some indecomposable, then you can take 2 beta-avoiding permutations and join them together like this, and the result will still avoid beta. This joining map is injective, and so this inequality on the counting sequence holds. Such a sequence is called supermultiplicative, and Fouquet's lemma implies that the growth rate exists. If beta is skew indecomposable, then a symmetric argument applies. This only half works for an involution class avoiding beta. If beta is some indecomposable, the argument is just fine, but if beta is skew indecomposable, then the construction creates non-involutions. So 4, 2, 3, 1 avoiding involutions have a growth rate, but what about 1, 3, 2, 4 avoiding involutions? The answer turns out to be yes. The idea is that we need a much more complicated way of weaving 2, 1, 3, 2, 4 avoiding involutions together. The strategy will be to decompose each of the involutions into a staircase diagram, then decompose them even further, and then weave them together. Begin by dragging down a square box from the top left corner, making it as big as possible while still avoiding the pattern 2, 1, 3. Next, we sweep a vertical line from the bottom left corner of the box rightward, going as far as possible while avoiding 1, 3, 2. And because we're working with involutions, we draw the mirror image of this box above. Now we sweep a horizontal line from the top right corner of the red box down as far as possible while avoiding 2, 1, 3, and repeat again with a red box. Before we describe the secondary decomposition, we now have to assume that we're working with an involution that has no fixed point that is also a right to left maximum. There can never be more than one of these, and this involution does have one. For now, we just delete it, and we'll worry about it later. Now, if you thought that I was glossing over too many details before, you're really going to love this part. The center box gets split into a symmetric top left and bottom right half, and the remaining entries, which must be strictly increasing, get lumped into a third box. Then we draw a dashed vertical line from the leftmost point in the bottom right box, and all of the points to the left in the box below get grouped together in yellow. All of the points above some point in the yellow box must be increasing, and they get grouped together in red, and then we group all the rest in orange. We repeat this process on the remaining stairs, observing that some of the boxes can be empty. The result is a secondary decomposition where every stair has been split into 3 blocks, one of which is guaranteed to be increasing. We can summarize this structure with the following picture. Now suppose that we have 2 1, 3, 2, 4 avoiding involutions, pi and sigma. In order to weave them together to get one big 1, 3, 2, 4 avoiding involution, we take apart their boxes and combine them like this. Now this is not as bad as it looks. The key is that all of the interleaving of entries from each individual permutation is preserved. Outlined here are the entries from pi, and the boxes are still arranged in the same relative order, just spread out. The same for the entries of sigma. The way this is built guarantees that the result is an involution, and with a lot of patience you can see that it still avoids 1, 3, 2, 4. From this large 1, 3, 2, 4 avoiding involution, we can actually unravel it to recover pi and sigma. Which means that if we consider this to be a map just on the 1, 3, 2, 4 avoiding involutions that don't have a fixed point that is also a right to left maximum, then this map is injective. Now this is not obvious, but we don't have the time to discuss the details here. Well, since this map is injective, just like in the case of regular permutation classes, that means that this sequence, the involutions without a fixed point that is also a right to left maximum, is supermultiplicative and has a growth rate. Calling this sequence an, and the sequence that we actually care about, all 1, 3, 2, 4 avoiding involutions, bn, we can show that bn is bounded between an and an plus n times an minus 1. Therefore, the growth rate of bn exists and must have the same value as the growth rate of an.